don't have to be beautiful to turn me on.
Here we are with Mr. Haas and special guest Tyler.
Hey, hi.
We're going to talk about exponential functions. We've been doing this in class, so let's just do a couple of practice here. Let's say the population of New Paltz is 15,000, seems about right. And let's say the population is increasing by 3% each year. I don't know if that's actually happening, but it's reasonable. So what does that really mean? That means that next year, the population is going to be 103% of what it is this year. The year after that, it's going to be 103% of what it was the previous year. So, in other words, if I take my 15,000, I'm going to multiply it by 103%, right? And for the next year, I want 103% again, and 103% again. You get where I'm going here?
I think I get it. That's good.
So, if I'm saying that's my population at any time, let's make this a little neater. If I'm saying, okay, I'm starting off with 15,000 people, I'm multiplying it by 103%. I don't want to have to write that percent sign there. What do I do, Tyler? What do I do if I want to write something without the percent sign?
Decimal over 2 places to the left.
Yeah, because that really just means divide by 100. So I'm going to multiplying it by 1.03. And if I want to figure out the population in X years, I'm going to multiply it by 1.03 X times. There's my exponential equation. Okay.
That's looking great.
So let's say, for example, what would the population be in 3 years? Well, now I can use this equation, right? So I've got P equals 15,000 times 1.03 to the third. I see you're grabbing your calculator. You don't think I can do this in my head, Mr. Haas?
That's going to be rough.
Well, I'm just going to write it out for fun. I mean, you obviously aren't going to do this, but that's really what that means. 3 years means I'm multiplying 15,000 times 1.03 3 times. The exponent is just a shorthand for that. What does that actually give us there, Mr.
So that is 16,390.905. Now, I'm not sure what that means in terms of people, but
Yeah, I don't want like body parts lying around.
Yeah,
Should we round that to the nearest human?
absolutely.
All right, so let's say about 16,391 is my population in 3 years.
That's terrific.
And there you go. Basically, whenever you have percent increase, you're going to have exponential growth. And there you have it.
There's another one, Ms. Stewart. You ready?
Ready?
You're having way too much fun.
I am having too much fun.
The population of Highland is 6,000. Is that really all it is?
Well, the Wikipedia said around 5,600.
Wikipedia said it must be true then.
See, it must be true. New Paltz has the university, so that's why our population
I don't know,
is bigger.
I just guessed it at 15,000.
I think it's pretty close.
At any rate, the population of Highland is 6,000 and is decreasing by 3%. Coincidentally also, maybe they're moving to New Paltz. I don't know if that's... So I'm going to write some kind of equation. I guess I could call it P for population, but I don't know. I like to use X's and Y's. Is that all right?
You're very old-fashioned.
Yeah, the Y is the population. This is my initial value, 6,000. It's decreasing by 3% each year. That means next year they're going to have 97%. Right? There's 100 minus 3%. Next year they're going to have 97% of what they had this year. And the next year it's going to be 97% of that. So I guess I could go times 97 times 97.97.
Very nice.
I should say, right?
Yeah.
Because it's 97%, but I'm writing it as a decimal.
That totally makes sense.
That's the whole thing?
That's the whole thing.
It's pretty easy.
It is.
Oh, all right. Should we do another one?
Absolutely.
Okay. Here's another one, Miss Stewart. It says the population of Kingston is about 25,000. Well, that's roughly correct.
Sure.
And is doubling. It's not doubling every year, though. It's doubling every 60 years. It's a little bit different. It's a little bit different.
Yeah.
That means in 60 years, they're going to have 50,000 people. Alright, okay, how that works. So I know how to start this. The current population is 25,000. And it's doubling. Well, that means that they're going to have 200%. So as a decimal, 200%, move it over 2 places. I think that's going to be a 2.
It's going to be a 2.
I'm pretty sure.
Which
That's
makes sense when you're doubling
times
something.
2, I guess
Times
that works.
2.
So they're doubling every 60 years. Sometimes students get this mixed up. Is it 60x? Is it x over 60? Is it 60 over x? Well, what do you think? I mean, how could I figure this out?
Well, let's see. You want to multiply by 2 when you plug in a 60. So when you plug in a 60, you want your exponent to be a 1.
Okay, so if I plug in a 60, let's try this.
Okay.
Well, let's see what happens. Yeah, okay. So what if I made this x over 60? Is that going to work? So in other words, after 60 years, I should have twice as many people. If I put in 60 years for x, that makes the exponent 1. 2 to the first is 2 times 25,000. Oh, that works.
It does
so
work.
how long would it take for it to have 4 times the amount of people? What would I have
Well,
to
we
put
want it to double again, so we want that exponent to be a 2. So I guess that would be 120
So does that work? If I
years.
stuck in 120, should double twice, because 120 divided by 60 is 2. 2 squared is 4 times 25. Oh, that works. So yeah, I never remember how that is, but you can always kind of, so x over 60 is how many years. That works.
Well done. I think you do remember, but
Well, yeah, okay, perhaps.
Here's an example that you probably have seen in science class. The half-life of carbon-14 is about 5,730 years. Write an equation which would represent the amount of carbon-14 left after X years. So something has died, something that was living has died. You want to measure the amount of carbon-14 that's left. Well, here we go. Mr. Haas, I'm going with your Y. So the amount of carbon-14 left would be, well, they didn't tell me what I started with, but when you're alive, I guess you can say you have 100% of your carbon-14. So can I just say 1 representing 100%? Okay, half-life, well that means that it's halving, right? Halving. So I'm multiplying that by a half. This is just like the problem that Mr. Haas just did. I'm not halving every year, I'm halving every 5,730 years. So let's figure out what that exponent is going to be. Again, I want this exponent, I want to have it once every 5,730 years. So I'm going to take the number of years and divide it by 5,730. Does that make sense?
Well, that makes sense. So in other words, every time I increase x by 5,730, that exponent actually increases by 1. That's really what's
That's
going
right.
on there. Is that what's
That's right.
happening?
Yeah.
I see.
And clearly, it's not like you have the amount of carbon-14 and suddenly 5,730 years come and boom, you're half. It's an incremental thing. So you can plug in any other numbers. You can plug in 1 or 2 or 3, as many years as you want, and you'll get some, it's decaying slowly, but it's not going to have half until a whole 5,000.
So now let's say the question said your initial amount of carbon-14 was 3 grams. What would you do for that?
Okay, so my initial amount of carbon-14 is 3 grams. Oh, okay. Well now, rather than thinking, oh, I have all of it, now I have a different starting value. So that would
Just
be
stick in a 3 there, and that's
stick in a 3,
all right.
and I know now that I'm counting how many grams I have. Everything else would be exactly the same. Boom.
That's terrific.
Thank you. All right, so staying in the science theme, we've got bacteria hanging out in the petri dish. They're doubling 10 times an hour. Woo!
That's a lot of bacteria.
That's a lot
They're
of
growing like
doubling
mad.
going on.
Sure.
If you start with 1,000 bacteria, how many would you have in X hours? Well, I think we can figure this out. So the number we're going to have in X hours is start with 1,000 bacteria. What am I multiplying that by? Well, it's doubling, so that seems like a 2. I'm doubling, right? But every hour. That would be doubling every hour. I'm doubling 10 times in an hour. So when I plug in a 1 in there, I really want it to be doubling not once, but 10 times. So what do I have to do to that exponent, Mr. Haas?
Well, I mean, when it was the other, what was it, x over 10? What would that mean? That would mean every 10
Every
hours, right?
10 hours
Yeah, so
I'm
that can't be. It
doubling.
must be maybe 10 times x.
Ah, I think so. Let's see if that makes sense. So in 1 hour, that would be, right? Y equals 1,000 times 2 to the 1 ton. Yeah, that's what I want. It's going to double 10 times. 1,000 times 2 times 2 times 2 times 2 times 2, 10 times. In 2 hours, I'm going to be doubling it 2 times, then 20 times. So yeah, that works. So really, you just need to think through the problem, see how many times you want that thing to be doubling to figure out your exponent. It can be a little tricky, but if you stop and think about it, you'll be in good shape.
All right, this is our last one, so stay with us, because this is an important one. Don't you
It
think,
is.
Ms. Stewart? 'Cause This is a
Absolutely.
little bit different.
It is.
So now we're giving you a table with some data in it, or data. I say data, but whatever. So here's my table, and I'm giving you 3 x values, 3 y values, and you have to know that it's exponential. This is exponential data. So I want to write some equation that models this data. Y equals, how's that for a starting point?
You're looking good.
That's great. Now, I don't have the initial value. I don't have the starting point. I mean, here's when x is 1, but I want when x is 0 is really what I need. I want that, it's called actually the y sub 0. It's the y value when x is 0. I don't know it. I'm just going to write y sub 0 as a little placeholder there. I need my base. Well, my base tells me what I have to multiply this guy by to get the next guy. So 12 times something gives me 27. 27 times something gives me 60.75. Another way of saying that is, if this times something gives me this, I guess I could divide, couldn't I?
Yes, you could.
12 times something gives me 27, so therefore 27 divided by 12 should give me the base. You want to do that for me, Ms.
I
Stewart?
will. I think it's 2.25.
27 divided by 12 is 2.25. 2.25. So 60.75, I could just check. 60.75 divided by 27 should also give me 2.25.
And it does. So it's exponential, all right.
Yes, it must be. So in other words, 12 times 2.25 gives me this. This times 2.25 gives me this, and so forth. It's an exponential equation. And is it going up by this amount every x? I don't think so. It seems to be going up by 2.25 every time x goes up by 2. We're going by 2's here.
We are.
See what's going on?
So you have to do something to that exponent.
Is that working for you?
Yes.
Right? Every interval of 2, every 2 years, if this was time, could be in years, my base is increasing by 2.25. I'm basically done here, except I don't have a starting value. Now, how am I going to figure that out? Ms. Stewart, what are you thinking?
You know, I'm thinking of good old-fashioned, like y equals mx plus b. If I have 2 points, I can just plug in 2 points and find what I'm
Sure,
missing.
I'll just pick some point. I think this looks like a nice point. I can pick any point, of course, but I like picking a point with 1 in it. Why not? So I'll put in a 1 for x and a 12 for y. So I have 12 equals y sub 0, 2.25 to the 1/2.
Beautiful. I'm grabbing the calculator.
So 2.25 to the 1/2, that's the square root of 2.25, which I can't do in my head. And then I have to do 12 divided by that, right? It's going to be 12 divided by 2.25 to the 1/2. It's going to give me my y sub 0. You want to just do the whole thing in one shot?
I
Ms.
will. It's a wonderful number.
Stewart? What do you got?
It's 8.
Oh, 8. Well, that works out nice, doesn't it?
Isn't
All right.
that
So I'm
nice?
going to write the whole equation. Y equals 8, 2.25, the 1/2. Oh, not 1/2, I'm sorry.
1/2 x, or,
To the x over 2,
X over
or
2.
1/2 x.
yeah,
Terrific.
very nicely done.